Put a cat in front of two doors. The first is tall, but barely wider than your palm. The second is comfortably wide, but so low it almost touches the floor. A human would measure both. A dog might inspect them. The cat does something stranger. It walks straight at the narrow door, compresses into a furry comma, and keeps going. But at the low door, it slows down. It may stop, sit, or search for another route. Cats squeeze behind refrigerators, under fences, and into containers that appear to contain less space than cat. But before a cat enters a gap, does it actually know the shape of the body it is about to put inside? When people hear self-awareness, they usually imagine a mirror. An animal sees a mark on its face, recognizes the reflection, and removes the mark. Pass or fail. Self-aware or not, but that bundles many different abilities into one dramatic test. A simpler kind of self-knowledge is body awareness, using information about your own size, shape, or weight before an action. You use it when you turn your shoulders before a narrow doorway. No mirror is required. The question is not, does the cat know who it is? It is, does the cat know what this body can do? In 2024, researchers analyzed 30 privately owned cats. Tests happened at home, because a strange laboratory is excellent for studying the underside of a bed. A cardboard panel blocked a doorway. The owner waited on the other side with food or a toy. To reach the owner, the cat had to use one opening. There were two versions. In one, the opening stayed 50 centimeters tall, while its width shrank across 5 trials: 13, 11, 9, 7, then 5 centimeters. In the other, the opening stayed 15 centimeters wide, while its height dropped from 43 centimeters to 15. If a cat used an internal estimate of its body, the key behavior should happen before contact. Slow down, stop, or choose another route. The cat's median chest width was about 11 centimeters, so the smallest vertical slit was less than half that width. From a human perspective, this looks like a closed door with a clerical error, but the cats generally approached even the narrowest openings, without a clear increase in advance hesitation. They arrived, tested the gap, and squeezed. There was a slight tendency to hesitate while moving through the narrower slits, but the pattern was not statistically strong. The important result is not that every cat passed every opening. It is that narrowing the slit did not produce a clear early warning response. That may look like poor planning. For a cat, it may be efficient planning. Why calculate a problem your shoulders can negotiate on arrival? Cats are built for complicated spaces. Their small, free-moving collarbones do not lock their shoulders into one rigid frame. Their bodies flex. They often move slowly through clutter, and their whiskers can provide close-range information when vision becomes less useful. The study did not test whether whiskers act like a tape measure, so we should not pretend that it did. But anatomy changes the price of being wrong. For a running dog, hitting a gap that is too small can be costly. For a cautious cat, touching a narrow edge and adjusting may be the sensible strategy. A narrow gap can be a cheap test. Approach first. Decide at the edge. Then the geometry rotated. The opening stayed wide, but became lower across 5 trials, ending at 15 centimeters. Now the behavior changed. Cats hesitated more while approaching the shortest opening. They also hesitated more while passing through the 2 shortest ones. In the final trials, they were more likely to inspect the panel, turn back, attempt to jump, or go over it. Taller cats chose these alternatives more often. This is the more interesting evidence for body size representation. Before fully entering, the cat behaved as though the relationship between its body and the opening mattered. Not every small space is the same problem. A cat can rotate and compress its shoulders. Lowering the entire body removes leg room, changes posture, and may make the animal feel more vulnerable. In earlier, similar experiments, dogs slowed before openings that were too small and sometimes chose a detour. That does not make dogs more self-aware or cats worse at geometry. It means the same doorway asks different questions of different bodies. For a faster, less flexible animal, deciding early can prevent a collision. For a flexible ambush predator that moves carefully through clutter, testing a vertical slit may cost almost nothing. A low tunnel is different. It forces a whole-body commitment. So the useful model is not a tiny cat in the brain holding a ruler. It is a decision rule, tall and narrow. Approach, feel, adjust. Wide and low. Compare, hesitate, perhaps jump. Trial and error is not the absence of intelligence. Sometimes it is intelligence refusing to do unnecessary paperwork. The study gives us a pattern, not a mind-reading machine. Only 30 cats were included in the analysis. Very large breeds and obese cats were excluded. The tests happened in different homes, so the researchers could not keep every starting distance identical, and the experiment cannot tell us whether cats lack a detailed representation of width or simply prefer not to use it when squeezing is easy. The result therefore suggests selective use of body size information. It does not prove that a cat carries an exact three-dimensional model of itself. Experience, whisker feedback, flexibility, caution, and body awareness may all contribute. That uncertainty is not a flaw in the story. It is the story. We imagine self-knowledge as one stable outline labeled me, but a moving animal needs something more practical. Can I pass, crouch, turn, or jump? The answer changes with the space. So does your cat know its shape? Probably not as one perfect diagram. It may know a collection of possible shapes, including not going through there. A cat may not carry a perfect picture of itself. It carries a moving answer. Can this body become the shape this space requires?